Hello everyone, and welcome back to another lecture video. In this lecture video, we are going to extend what we learned in the last video when we talked about general solid elements to a very particular element type called triangular elements. Now again, this lecture is actually going to be an extension of what we learned in the previous lecture. So remember that for a general solid element, we obtained two things. One was an expression for the stiffness matrix, and the other was an expression for the nodal forces vector. And those looked like the following, where our stiffness matrix can be found by simply taking B transpose multiplied by C multiplied by B and then integrated over the element. And in the last lecture, we talked what exactly B is, and we also talked what exactly C is. So there was no real unknowns there. And then we also said that the nodal forces vector can be obtained by integrating the traction vectors over the surfaces, as well as the body forces over the element itself. But at the end of the last lecture, we kind of ended off by saying, all right, this is great. We have nice expressions for our stiffnesses as well as our nodal forces vector, but we had a problem, and that was this. Our B matrix as well as our N matrix, those were functions of the shape functions, and we didn't exactly specify what the shape functions are. We said that we need the shape functions, but we also said that those shape functions are actually a function of two things. One is the element type selected, and the other one is the geometric order of that element type. Well, in this lecture, we are going to examine one of the most common element types, and that is a triangular solid element. So again, we are going to examine triangular elements. Now, when it comes to triangular elements, there's going to be two types of geometric order that we are going to examine in this lecture. The first one is a linear triangular element. So if we look at this element, it's simply a right triangle, and it has three nodes, one node located at each of the corners of the element. The second one we're going to look at is a quadratic triangular element. So unlike the linear triangular element, this one actually has 6 nodes. It still has the nodes at the corner of the element, but we introduce a second node at the midspan at each of the surfaces of the element. So this is what we are going to examine here today. So again, just a little recap. We said that our B matrix and our N matrix are a function of the shape functions, and that depends on what element type is selected, as well as the geometric order of the element. Well, again, in this particular lecture, we are going to look at triangular elements, and more specifically, we are going to look at a geometric order of a linear triangular element and a quadratic triangular element. So let's start off with the first case, which is the linear triangular element. Now, these linear triangular elements, as we're going to see, have a very specific property that makes them rather unique. So sometimes these are actually referred to as a constant strain triangular element or simply a CST element. Now, again, just like before, we said that we had our element here, and it has 3 nodes. So typically when we are numbering these nodes, we begin at the bottom left corner, and we go around the element counterclockwise. So at the bottom left corner, I have node 1. On the bottom right corner, I have node 2. And then finally at the top, I have node number 3. Now, for simplicity of calculations, what I'm going to do is I'm going to say that the two lengths of this triangle are simply 1 unit long. Now, we said that we have a linear triangular element, and that linear idea is related to the geometric order of our approximation function. So as you guys may guess, if we have a linear triangular element, well, we are going to have a linear approximation function assumed between the nodes. And this is why we call it a linear triangular element. Nice and simple. So for this particular element, we are going to say that our displacement function, which again is a vector consisting of components u and v, or basically the displacement in the horizontal direction and the displacement in the vertical direction. And since we are assuming a nice linear approximation, we are going to say that each component can be approximated as a0 plus a1 times x1 plus a2 times x2. So that would be for the horizontal component. And if we were dealing with the vertical component, it would be b0 plus b1 times x1 plus b2 times x2. Now, we also said in the last lecture that this is a particular problem because this right here, this is a general displacement function for the entire element. But in the finite element method, we want to express our approximation function in terms of two things. One is the nodal displacement, so that would be my displacements at those 3 nodes, as well as the shape functions. So what we're going to do is we're going to take the scenario we see there on the left, and we are going to convert it to this scenario we see here on the right, where we're not approximating the displacement at every point along the element. We are just concerned with the displacements at the nodes of the element. For instance, at node 1 there, we know it has a degree of freedom u1, which is the horizontal displacement of node 1, and a degree of freedom v1, which is the vertical displacement of that element. So we can conclude that each node here in this element has 2 degrees of freedom. So from here, we're going to take that approximation function, which is a function of a naught and b naught, etc., and we are going to convert it into the following, where instead of a naught, a1, a2, and b naught, b1, b2, we are going to convert it so that it is a function of the nodal displacements, u1, u2, u3, v1, v2, v3, and our shape function. So we can see in here that we also have n1, n2, and n3. Those are going to be our shape functions, and those are the things that we did not define in our previous lecture, but now we are going to define them. So if we were to look at this approximation function, we have our nodal displacements, which is something that we're trying to solve for, and our shape functions. So we're actually going to need to figure out what those shape functions are before we can proceed to finding those nodal displacements. So the question becomes, how do we determine those shape functions? Well, it's actually rather simple. We're going to use the exact same process we used for those one-dimensional bar or truss elements. Now, this can be a little bit confusing, so what I did is, in the description down below, I'm going to include some examples of how to actually determine these shape functions, just in case things are a little bit blurry after we go through here. So if we're trying to determine a shape function, we can utilize 2 properties of a shape function that makes things rather easy to visualize, and that is this. If I'm looking at a shape function for a particular node, in this case I'm looking at the shape function for node 1, hence n1. Now, this shape function for node 1 must have a value of 1 at node 1, and it must have a value of 0 at the other 2 nodes. So for this particular shape function, it must be a plane, which again has a value of 1 at node 1, and a value of 0 at the other 2 nodes. Now, finding an equation for this plane, well, we'd find out that n1 is actually equal to 1 minus x1 minus x2. Now again, if it's not entirely clear where exactly this came from, don't worry, I will include an example in the description down below on how exactly we can obtain these shape functions. Now, if we were to move on to n2, it's going to be the exact same process, but the only difference is since we're dealing with node 2 now, the shape function must have a value of 1 at node 2 and a value of 0 at the other 2 nodes. So we know it's going to look something like this. And in this case, our shape function n2, it's simply going to be x1. Moving on to our final node, again, since we're dealing with node 3, we know that the shape function must have a value of 1 at node 3 and a value of 0 at the other 2 nodes. Therefore, the shape function is going to look something like this, and we know that our shape function n3 is simply going to be x2. Now that we know all the shape functions, we can actually determine what our n matrix is. So recall from the last lecture that our n matrix was simply n1, 0, n2, 0, n3, 0, which corresponds to basically the horizontal or the u components. And then we have 0, n1, 0, n2, 0, n3, and those corresponded to the vertical components or the v components. Now, since we look at this and we say, all right, well, it's only a function of n1, n2, and n3, I know what those are, I can substitute those values in and actually gain a nice expression for my n matrix. Again, all I did was I took my shape functions, which I defined above, and I substituted them into their correct spots. And we said that this is great because once we know what those shape functions are, we can actually use it to determine something called that B matrix, which again related the nodal displacements to the strains of our elements. And we said that our B matrix actually has the following format. Now, yes, this is very gross. No one wants to deal with this, but it's nice because again, one of the things that we said was that this B matrix is very repetitive. Every 2 columns is always associated with the same shape function. For instance, if I look at my first 2 columns here, well, I'm only dealing with my shape function n1. I look at the next 2 columns, well, again, I'm only dealing with my shape function n2, and then so on. So our next 2 columns, those are going to be n3. And if I had n4, n5, and n6, etc., well, I just keep adding on 2 more columns to my B matrix. Now, if we look here, again, it's just a function of n1, n2, and n3, and we know what n1, n2, and n3 are. Therefore, if we want to take the partial derivatives, well, it's actually not a problem. We get our B matrix is equal to the following. Now, one of the nice things about this B matrix for a linear triangular element or a CST element is that it's actually constant. If we look here, it's just a bunch of 1s and negative 1s. It's not a function of x1 or x2. Now, this is particularly important because if we look at what B actually does, remember, it's the relationship between the strains and the nodal displacements. Now, if our B is constant and our nodal displacements are, of course, going to be constant, well, therefore, this indicates that we actually have a constant strain throughout this element. And this is why we call it a CST or a constant strain triangle. because we actually result in constant strains throughout this element. Now, we said that we can take our B matrix and actually use it to calculate the stiffness matrix. So again, from our general solid elements lecture, we concluded that the stiffness matrix can be found by simply transposing B, multiplying it by C, multiplying it by B again, and then integrating over the element. So if we look here, we say, all right, well, that B matrix, that's no problem. We defined that on the previous page. The only real problem that we have right now is that C matrix. And we said that, well, for a 2D case, this actually depends on if we assume plane stress or plane strain. So if you guys are using a finite element program such as Abacus or ANSYS, and you guys are doing one of these 2D analysis, well, one of the things that you'll actually have to specify is if we're assuming plane stress or plane strain. Now, Abacus, for example, by default will always assume plane stress, but you guys can go into the element options and modify it if you guys wish. Now, if we assume plane strain and a constant into the page thickness t, we can actually calculate our stiffness matrix as the following. And yes, this looks really gross, but again, it's just the combination of those three components that we had above. First, we have B transpose, then we have C. So again, this is going to be our constitutive law for plane strain. If it was plane stress, we would have a different constitutive law. And then we follow it up with B itself. And then what we do is we put all this together, and then we integrate it from 0 to 1 minus x2 in the x1 direction, and then from 0 to 1 in the x2 direction. And this actually results in a nice 6 by 6 matrix. Why is it 6 by 6? Well, we have 3 nodes, and each one of those nodes has 2 degrees of freedom. So we take 3, multiply it by 2, we get 6, and that's the reason why it's actually 6 by 6. Now, I'm going to also let you guys in on a little secret here. This element right here, this formulation, actually kind of sucks. And the reason why is we have that double integral there. We assumed a nice into the page thickness t, so that kind of simplified things a little bit. But we're still left with that double integral. And if we're integrating each one of these components, well, of course, it's going to take forever. Now, if you guys have used commercial software such as Abacus or ANSYS, we know that it actually doesn't take forever for a single element. It's actually really, really fast. Now, that's one of the things we are going to discuss in a future lecture when we start talking about isoparametric elements. So from a theoretical standpoint, this is exactly how we get the stiffness matrix. Everything in here right now we can actually define. As we can see, we only need the elastic modulus E, Poisson's ratio nu, and that into the page thickness T. We're actually good to go. We can solve for this right now, right here. But the problem is taking those integrals takes a lot of time. And I don't know about you guys, but I'm always running out of time. You guys probably are too. You guys don't want things to take a long time. So one of the things we're going to discuss moving forward is how can we obtain this stiffness for this element without actually integrating. So that's one of the things we're going to discuss in the future. But for right now, from a purely theoretical standpoint, this is exactly how it's done to obtain that stiffness. Moving on, we said in order to get those nodal displacements, we need a stiffness matrix, but we also need our nodal forces vector. So what we're going to do is we're going to look at, all right, well, now that I know all of the components that I didn't have before, how can I calculate those nodal forces due to body forces as well as traction vectors? So let's start with body forces. So the formula is very simple. All I'm going to do is take my N matrix transpose and multiply it by rho B and then integrate it over the element. So I'm going to get something just like this. Now, the question becomes, Clayton, what exactly is B1 and B2? Well, those would be gravity components. So the whole thing of body forces, this is basically accounting for things like gravity. So if I was dealing with gravity in the specific case, B1 would be 0 because we don't have gravity in the horizontal direction. Could you imagine if we did, how things would get very interesting very fast? Now, in the B2 direction, or the vertical direction, we'd specify a value such as negative 9.81 meters per second squared. So that's exactly what these body forces are. Now, the thing to keep in mind here is that we're actually integrating over the element. So that double integral that we had before on the previous slide for the stiffness matrix, well, it actually also applies for this body forces vector. Now, one of the things I get from a lot of students is they say, all right, well, I know how to calculate these body forces, but what exactly am I doing with this integral? Well, it's actually very simple. If I had this element here, well, we know that this element is subjected to gravity, which acts over the volume of this element, which is why we actually integrated over the volume of the element. Now, the problem is when I'm actually solving my system, remember, it's a function of the stiffness matrix as well as the nodal forces and nodal displacements. It's not a function of just all the forces throughout the element. So what we need to do is we're taking these body forces that are due to things like gravity, and we're actually converting them into equivalent nodal loads. So we're taking that gravity load that is present throughout the entire element, and we are simplifying, creating an equivalent load representing that gravity located at our nodes, so we can account for them when we're solving our system. Now, on the other side, we have traction vectors. So these would be things due to something like distributed load throughout our element. As we can see, the formulation is almost identical. The only difference really being is we're integrating over a surface, and instead of rho b, we have Tn, which is our traction vector. So when we're solving for it, it's actually going to look very similar. The only difference is instead of b1, b2, we now have t1, t2, and we are now integrating over the surface. You might be saying, Clayton, why exactly are we doing that? Well, traction vectors are actually like things like a distributed load. If I had a distributed load on a beam, well, of course, I'm not going to integrate that distributed load over the volume of the beam. I'm just going to integrate that distributed load over the actual surface of the beam. So that integral that we're taking over the surface, even though I have it as 0 to 1, this is going to change depending on where our distributed load acts. This 0 to 1 here would represent something like this, where my distributed load acts on that vertical surface, so along x2. And what I'm doing is I'm taking that distributed load, which acts throughout that surface of the element, and again, all I'm doing is converting it to an equivalent nodal forces. Now that was triangular elements, and these were perhaps the most simple case. All the cases moving forward, so in the rest of this video, we're going to look at quadratic triangular elements, and in the next video, we're going to look at quadrilateral elements. Well, things are going to get a lot more messy, as you guys will see. So if we're looking at quadratic triangular elements, we said, all right, well, this isn't actually that big of a problem. The only real difference between a quadratic triangular element and a linear quadratic element is we're introducing those nodes at the midspan of each of the surfaces of this triangle. So in total here, we are going to have 6 nodes. So rather than 1, 2, 3, we have 1, 2, 3, and then 4, 5, 6. Now, one of the things you guys are going to see moving forward is the number of nodes we have is actually equal to the number of A coefficients we can assume in our approximation. Now, as you guys may have guessed, if we have a quadratic triangular element, well, we are going to use a quadratic approximation function. So before we had A0 plus A1 times x1 plus A2 times x2. Well, now we're adding an additional 3 terms, so we have a3 x1 times x2 plus a4 times x1 squared plus a5 times x2 squared. And again, if we look here, we have 6 nodes, and we actually have 6 coefficients in front of each one of these approximations. And the reason why is because for each one of these approximations, remember that we write them in terms of shape functions. So if we have 6 nodes, we have 6 shape functions, therefore we're allowed to have 6 coefficients. So kind of going on what I was just saying there is instead of having these general approximation functions, we know that we are more interested in our nodal displacements rather than our general displacement field. So what we're going to do is we're going to look at the nodal displacements for each one of these nodes, and each one of these nodes has 2 degrees of freedom. Therefore, I can take my general approximation function and rewrite it into the following form, where I have u1 times n1 plus u2 times n2 plus u3 times n3 plus u4 times n4 plus u5 times n5 plus u6 times n6. Wow, that was a real mouthful. I got a dry throat just saying that, but hopefully I can make it through the rest of these slides. So again, we see here that we have 6 shape functions, 1 for each one of the nodes. Now our nodal displacements, u1 through u6 and v1 through v6, those are what we're trying to solve for. So in order to do that, we actually have to figure out what our 6 shape functions are. And, well, as you guys may have guessed, we are going to use the exact same procedure as we did in our 1D elements. Now again, if you guys are confused where I'm getting these from, don't worry. I will include an example in the description below showing you guys exactly how to obtain these shape function equations. So if we were to look at the shape function n1, which corresponds to node 1, the same rules apply here, except things get a little bit more complicated. So of course, it has to have a value of 1 at node 1 and a value of 0 at the other nodes. Now, of course, a linear approximation would never be able to do this. This is why we go to a quadratic approximation. So we know that a shape function plane is actually going to look something like this, where it gets a little bit complicated. Now, this plane here can be represented by the following equation, where n1 is equal to 1 minus x1 minus x2 multiplied by 1 minus 2x1 minus 2x2. And if I were to repeat this process for the remaining 5 nodes, I get the following shape functions. Now remember, one of the things that we're going to do with these shape functions is actually take their partial derivatives and summarize all those in our B matrix. So as you guys may guess, well, things are going to get really, really messy. So if we were to start with our n matrix, again, that's the nice simple case where it's just n1, 0, n2, 0, n3, 0, etc. And then our second row is 0, n1, 0, n2, 0, n3, etc., etc. Well, that's not a problem at all. The only problem I seem to be having with this n matrix, well, I'm running out of colors. Again, I like showing you guys the colors of each one of these shape functions because it allows for you guys to see the repetitive nature of these n matrices as well as our B matrix. So as we can see here, if we had an n7, n8, n9, etc., etc., well, all we need to do is just keep adding on additional columns to this n matrix. It's actually not a problem. It looks complex, but it's actually not too bad. So from there, we can also calculate the B matrix for our elements. And again, it looks really gross. It makes you guys probably a little bit sad, but don't worry. Again, really repetitive. So our first two columns, they just deal with n1. Our second two columns just deal with n2. Etc., etc. So again, if I had an n7, n8, n9, etc., well, I just keep adding additional columns to this B matrix. Now, of course, I'm not going to solve it. I don't think that there's a PowerPoint big enough allowing me to show you guys the solution for the B matrix in this particular case. So we're just going to move on to the stiffness matrix and our nodal forces. So since we know our shape function matrix n and our B matrix, well, we can calculate everything we need. Looking at our stiffness matrix, again, exact same formula. The only difference here is B is now different, and that's it. So of course, B transpose multiplied by C multiplied by B transpose, it's not a big deal. The only thing that we don't really know is going to be that C. But we said, well, if we assume plane stress or plane strain, we actually do know what C is. That's actually not going to be a problem. Now, if you guys remember from the linear case, we had a 6 by 6 matrix. Well, in this case, this will result in a 12 by 12 matrix. The reason why it's 12 by 12 is now we have 6 nodes, and each one of those nodes has 2 degrees of freedom. 6 times 2 is 12, therefore our matrix is 12 by 12. So just going higher up in that geometric order, it results in a much bigger matrix. However, the approximation will be better. So this is one of the things that we're going to have to try and figure out when we're dealing with our own finite element program. And this is also one of the things that there's not always a set answer in. The question is, do I use more linear elements because of course they take less computation time, or do I use fewer quadratic elements? They will take more computation time, but in the end there's going to be that trade-off where you get that increased accuracy. So that's one of the things we're going to have to figure out later on in the course. So then the other thing we can do is find our nodal forces. Of course, we have our n matrix, and because our n matrix is much bigger, this results in a 12 component vector. And as we're seeing, the complexity of these calculations is proportional to the degrees of freedom of the element. So I'm saying degrees of freedom of the element. I'm not saying the degrees of freedom of the nodes. So of course, each node has 2 degrees of freedom. But to find the degrees of freedom of the element itself, we take the number of nodes, multiply them by the degrees of freedom per each one of those nodes, and we get the degrees of freedom of the element. So in this case, we would say that these elements have 12 degrees of freedom. 6 nodes, each node having 2 degrees of freedom. Now, the thing to keep in mind is that 12 by 12 matrix that we have above here, that was just for a 2-dimensional case. A simple 2-dimensional element is a 12 by 12 matrix. Can you imagine what a 3D element is going to take? Now, before we kind of discuss what the 3D elements look like, again, I really want to emphasize something. Currently, our stiffness matrix there, we have that integral over the element. This will take a long time. Especially if we're dealing with a 12 by 12 matrix, it's not going to be it's not going to be fun for a computer to try and take a double integral of a 12 by 12 matrix. So as we're going to see later on, we are going to discuss ways on obtaining the stiffnesses of these matrices without actually using the need to integrate throughout the elements. But that is something for later on. I just want to clarify it because if you guys are coming here looking for those isoparametric formulations and you're not seeing them, well, I'm just going to let you know that right now we're looking purely at the theory, and in later videos we're going to look at, all right, here's our theory, how can we simplify it to make things run a little bit faster? So the final thing I'm going to touch up here is those 3D triangular elements I kind of hinted towards. The 3D version of a triangular element is actually referred to as a tetrahedron element, and they're actually very simple. So of course we're going to look at 2 cases, linear and quadratic. For the linear case, we can see that we have 4 nodes. But the only difference is each one of these nodes now has 3 degrees of freedom. Makes sense because in 3 dimensions, we're introducing that extra dimension that we're going to have to account for. Well, we're going to have 3 degrees of freedom. So in total, this will result in a 12 by 12 matrix, and that's just through a linear approximation. If we were to increase it to a quadratic approximation, well, of course, we can see that we now have 10 nodes, and each one of these nodes is going to have 3 degrees of freedom. Now, if we were to take 10 multiplied by 3, this would indicate that the size of our stiffness matrix for this particular element is going to be 30 by 30. Now again, that's just one particular element. When we're dealing with the finite element analysis method, we actually typically have thousands of elements. It's not just usually 1 or 2 elements, it's usually hundreds, if not thousands of elements. So if we have 1,000 elements and each one is 30 by 30, well, I don't want to be taking that double integral. Therefore, we are going to start introducing ways that we can calculate the stiffnesses of these matrices without the need of actual integration. Now, if we look at these 3D elements, they're actually the same process as the two-dimensional elements. All we need to do is find the shape functions for each one of the nodes. From there, we can find our B matrix, and then from the B matrix, we can find our stiffness matrix and then solve the system. So it's actually really nice for these solid elements because even though each one looks different, here we have triangular elements, tetrahedron elements, later on we'll explore quadrilateral and brick elements. The procedure for each one of these is exactly the same, which is nice. The only thing that really differs is the number of nodes that we have and the approximation function associated with each of those nodes. But yeah, that's it for triangular elements. Thank you guys so much for listening. I really appreciate it. I will see you guys in the next lecture video.